Hi, I'm Dr. Bill Fortney. I'm the director of NC State's Mechanical Engineering Systems BSc program, and one of my passions is to help students realize that they can become more effective designers if they will take their traditional engineering skills and combine them with some of the tools from systems perspective. I've done the video, the systems perspective, and also my book, Engineering Design, the Systems Perspective. And what follows is a recording that I made as parting words for my systems design class. And my hope is that you will put these words into practice and they will help you become a more effective designer as well. The systems approach to design is a valuable tool that's going to help you as an engineer as you move forward. So before we depart this semester, I wanted to take just a few minutes to just hit some key concepts to make sure that you're walking away with. Okay. So the first one is to make sure you understand, what do we do as engineers? What is your role going to be? There's going to be some complex problem situation. A customer with a need in that situation is going to come to you, the engineer, and what they're going to want you to do is to completely satisfy their need. They may ask for a particular product or whatever, but what they really want is for you to understand their need and satisfy it. Early in your career, the customer is going to be your boss. Your boss is going to come to you with something, and they want you to understand and satisfy their need. What they want you really to do, especially if what you're doing is designing a product, is they want you to study their situation, understand their need, and define requirements that are then going to drive your engineering design to create a product that satisfies their need. That's what we do as engineers, and that's what you did this semester. Okay, another key concept I want you to walk away with is the whole idea of systems. A system is a group of elements interacting, acting as a whole to achieve a common objective, and that common objective is defined by the wider system. Systems are always a part of something else, and that something else drives what is important to that system, what that system needs to be. And as engineers, we work with systems. Everything we interact with is a system. So it's critical that you begin to understand that and begin to look around to see those interactions, to see that the elements, the things that you're working with, aren't independent, and that your goal is to create the best wider system, not the individual piece that you're working on. And then as part of that, we introduce the whole idea of the analytical approach versus the systems approach. All of our engineering classes are based upon the analytical approach. We take the item apart, we study it, we assemble that knowledge back into a knowledge of the whole. And it works great. It works great for the individual components. But with systems, when we take the item apart, we lose the context. When we lose the context, we lose that wider system and the purpose and what's really required of our system. So that's why we also bring alongside the systems approach, where we identify that wider system. We understand it, and we transfer that understanding into what's needed of our system. And the thing I want to make sure that you realize is that these two approaches go hand in hand, that your analytical engineering design skills are critical. They are the things that will allow you to solve complex problems. But in addition to those technical skills, I encourage you to also develop your systems knowledge and your ability to look at the wider system so that when you're working on the details, you're taking all of these other pieces into account. They work together. Okay, and then kind of pulling these ideas together, we brought in the 4 cardinal rules for an effective design. If you could walk away this semester with these in your mind, using these when you're at work designing, you would make me a very happy man. Just the simple idea that when you've got a problem to solve, you understand the wider system. It contains what you're working on. You identify it, you understand it, and you determine what that wider system wants out of the piece that you're working on, and then transfer that into requirements for your piece. The other thing is you realize because you're working with systems, your piece isn't alone, so you understand the elements you interact with. You understand what they want from your system, how you influence them. You transfer that knowledge into what's required of your item. You also realize you're trying to create the best whole, not just your part. And then finally, from time to time, you lift your head from all the details, you step back, you look around, and you remember the system, and you take that into the knowledge when you go back to working on all the details. Those key ideas are things that I want you to walk away from and begin to use every day in your engineering practice. Okay, so these key ideas here, we actually put into practice this semester on your project. So we had a complex problem situation. Mix It Up came to us. They're a company that makes molded plastic parts. They have a flexible concept in their facility. And what they basically do is their plant consists of a production area, receiving area. Receiving takes in bulk powder. It processes it, produces 2 different types. That goes to the production area, and they produce molded parts. Mix It Up had already automated part of their facility, and they came to us exploring automation for receiving. And we learned that in receiving, there's the powder processing and then everything else. Powder processing is where we were focused, and they take in 2 types of powder. They dry it, they inspect it, then they output defective powder, the 2 kinds of powder ready for production, and data. And their vision for a new system was, currently they have this work management system that tells the operator when it's time to go and inspect powder, or take a temperature, or deliver barrels of powder to the drying area. Their vision is that our device has a home base. The work management tells it when a job needs to be done. It maneuvers around the plant. There's a 9-inch clear aisle through the facility, and it goes and it performs each of the service. When it's not operating, it goes back home. So, mix it up, a customer came to us with a need. Their drying system was running out of powder. Their powder was dried improperly and labeled wrong. The powder was being burned, and they had defective powder entering production. They wanted us to satisfy that need using an AGV. It was our job to study, to understand their need, and to deliver a product back, whether it was an AGV or not, that would actually satisfy that need. And we used this basic 6-step engineering design process to do that. So the first thing we did is we studied their situation to define requirements. We looked at our device like a black box, and we said, what would our device have to do to satisfy their need? And we defined requirements. From then, we entered in conceptual design, where we looked at those requirements and we conceptualized, we developed a system that would meet their needs. And so we did our basic design work there. We left conceptual design by actually architecting that system into subsystems. We divided it into subsystems so expertise could be put on each subsystem, as well as so that we could split up the workload. So then we entered what we typically call our detailed design. This is where the engineering design really starts coming in, and we started doing the details of designing each of those subsystems. We continued designing those, moving down into detailed design, where we're actually designing all the details of the components. When all that was done, we had a critical design review where our design was approved. Everybody said, yep, it's all perfect. It's ready to go to production. And so that's when we started our fabrication and testing. And with the systems approach, what we did is we started with the components. We said, okay, let's check the components against any component requirements to make sure that they're good before we then take those components and build them into the subsystems. Let's check each of those subsystems against any subsystem requirements before we build them all up into the full system. Now let's take the system, check it against our system requirements before we take it and implement it into the facility. So you see, it's that process that allows us to take the customer need, embed it all the way down into our design, even into our components, build those back up, and have a system in the end that meet the customer's needs. For example, the customer had a need where we had to take a temperature every 5 minutes. Well, when we started down here working on our conceptual design, one of our subsystems drove around and got the vehicle to the location. Another subsystem took temperature. So for that 5 minutes, we split that time up. 2 minutes was given to the subsystem that actually took the temperature, 3 to the subsystem that was driving around. Well, when we were down here starting to work on our detailed design, we realized that, okay, to take a temperature, there were some things we had to do. We had to go out, we had to get the probe located and device, we had to retract. So we had about 30 seconds to actually take the temperature. So that created a component requirement for the device that's taking the temperature. It needed to be able to respond within 30 seconds. So you see how that customer need got translated all the way down into a requirement for a component. And so that way, when we got that component in, the first thing we're going to do is we're going to check that component to make sure that its response time really is 30 seconds. Because if it's not good, we don't want to go ahead and build it up into this subsystem. It was good, so we build it up into this subsystem, and then we check to make sure that this subsystem can take a temperature in 2 minutes. Yes, it can. So now it's combined with the other subsystems in the system. We now check and make sure that the system can take a temperature every 5 minutes. So you see, that's how the customer's need gets translated all the way down and back around, and we ensure that we truly do satisfy the customer's need in what we deliver. So this is the engineering design process that we followed and that you will follow every time you've got an engineering design that you need to create. Okay, so let's focus on how do we actually go about doing this. So we're going to start with requirements definition. And we had these 5 steps that we followed to understand the customer's need, develop requirements that we could then use in our design. And so these 5 steps led us through understanding everything that was necessary to satisfy the customer's need. That's what requirements definition is all about. And that's wants and needs. We didn't try to separate as we were going through. And then what we do is we look at those in light of the whole idea of the 3-legged stool of project success, where the idea is that cost, performance, and schedule are all related. You can't change one without affecting the other. If I need to get it done in less time, I'm either going to have to pay more or I'm going to have to sacrifice on performance. If I have less money, I'm going to have to sacrifice one of these. So what we do is we look at all the things the customer wanted, and we say, okay, what can we deliver in the time that we have and the cost budget that we have? Are there some of these wants and needs that we can't deliver with these other constraints? So based on that and conversations with the customer, we determine the specific wants and needs that will be addressed by our system. Those are requirements. The other items are things we agree with the customer that are going to be left out. And those requirements basically come in the form of formal requirements and constraints, design parameters, things that me and you as the designer and the customer, we agree will be in place that we can count on, and then our interface control document, our physical and our logical interfaces. Our requirements reference this so that these interfaces are binding just like the requirements are. So you see, that is the process that we went through to get the requirements that we use and will go through and drive us all the way through design. And when we do that, these steps have taken us all the way through defining requirements. And we're left with all of these items. We've got the things from early on, our requirements, our design parameters, all those get collected in the operational concept document and presented at SRR to validate our requirements. SRR is our time to make sure the customer and us agree, yes, these are the requirements, you understand my problem properly, and it's okay to go forward and start designing. Okay, so we finished requirements definition, and then we moved into conceptual design. So with the conceptual design, we're bringing in our understanding of the customer's needs, and we then are designing a system, the concept for a system, that will meet that need. So we're looking at all of their needs, we're looking at all the aspects, we're considering many alternatives until we come together and create a concept for a design that will meet their need. That's what we do at concept design. The other thing we're doing with that is, part of systems architecting is as we break it into subsystems, we take all of the functions that the system has to do and we have to allocate those to a subsystem. We want to make sure that nothing gets left out and that everybody knows what they're responsible for. Because remember, very often these subsystems are different companies. So we want to make sure it's very clear that everything is covered, each company knows what they're responsible for. The other thing we had to do was we had hardware limitations, and so we had to decide which subsystems are going to be on which computer, because we had to have two computers. Okay, so after conceptual design, we then move into preliminary design and detailed design. And these steps are where your engineering fundamental courses, this is where you're really going to begin to use those because you're doing detailed engineering design. A lot of times people will call this conceptual design. These two phases, they'll call both of those detailed design. Okay, so going into preliminary design, we have system level requirements. We have a concept for our design. And the first thing that we're going to do is we're going to do subsystem requirements definition. Because if you remember, we started out at the very top defining the customer's need into requirements. We now have a concept. We have multiple subsystems. In our case, we have 3 subsystems. So before we actually start designing those, just like before we did conceptual design, we're going to do requirements definition on that subsystem to make sure we have a clear understanding of what it is that subsystem needs to do. So we're going to transfer from the system level the functions that our subsystem has to do, requirements from the system level, interface information from the system level, design parameters, evaluation criteria from the systems level. So we're going to define requirements for each of those subsystems. That's then what we'll use as we then do subsystem design. So now, each of those subsystems, we're going to start and begin to work on designing those, working out all the details of those. As we do, we're going to run across requirements. When we do, we're going to write those down as subsystem requirements. So for example, just a couple, we have a system requirement that it's got to send a temperature within 5 minutes. Well, we already saw the example. That means the drive subsystem is going to get some of that 5 minutes. The temperature is going to get some more. Another one was we had a weight requirement. Well, that weight requirement has to get defined to each subsystem. Now, it's going to be hard to do this allocation before we begin to start working on the details of these. So as we work on the details, we know enough to begin to define these requirements. The other thing that we're going to do as we're working, we're going to come across interfaces. When we do, we document those in our ICD. We're for sure going to have to document how we connect to other subsystems and our space allocation with those. Also, while we're doing the detailed design, we're going to come across situations where we need a component requirement like the temperature response. Specifying that temperature response is what allowed us, as we were designing this, to be able to make sure we took the temperature in 2 minutes. That, along with drive being able to get there in 3 minutes, is what allowed us to meet the system level need. So we saw before it traveling down. As we're doing this detailed design, this is how requirements get passed back up to make sure that what we're designing down here is going to allow us to meet the customer's need that existed at the very, very beginning so that we make them happy when it's all over. Okay, so while we're doing this detailed design, again, that's your engineering design. You're going to be working more and more on that in your courses. But just a few reminders. 1, remember design thinking. What before how. Understand what you're trying to do, and this is at every level, whether it's concept design, whether it's on one of the subsystems, whether it's on one of the components, whether you're doing conceptual, preliminary, or detailed, wherever you are with design, for every decision, understand what, brainstorm ways to do it. You're usually going to have to research. Then you analyze those. Analyzing usually means you got to build a prototype. You got to test. You got to try things out. Evaluate those based upon what's important to the customer, and then pick the best. That's design thinking that you want to use all the way through. You also want to remember when you're doing these designs, the 4 cardinal rules for design, we talked about those. The last one, from time to time, lift your head. When you're down doing strength analysis of this bolt and on this, it's so easy to get lost, so stop. And a good thing to do is go back to these documents you created early on and let them give you that big picture. We also want to remember what before how, big picture before the details. Be thinking of the whole before you just get lost in the parts. So just tips for while you're actually going through designing. And a tool that we have as we're going through this, we have design reviews. Design reviews is a chance for your peers, for other smart people to look at what you're doing and see if they see things that you're missing. So at concept review, you can think about your design. It's like architectural drawings. You have the big picture, you have a concept fleshed out with enough detail for people to see that it's feasible and it'll meet all their requirements. At PDR, it's like a floor plan where you know exactly where everything is, you know how things are going to connect, you know most of the sensors that you're using, your hardware. It's about, your design is about 85% defined. And then you have CDR, where it's like construction drawings. It's ready for the building to be built. Your design, you have engineering drawings, you have a bill of material with every part. Every component is selected. If you have components that have specific requirements, you have specifications for those. Your design is ready to go into production, a critical design review. And so these were another tool that helped us during design. So you see, this process allowed us to start with the customer's need and work it all the way down through. You started with system requirements, you came up with a concept. You broke that into subsystems and had subsystem requirements. You then began to work on designing the subsystems. You continued to work on more detail until you were designing every component. As you were doing that, you had some component requirements. You continued following this process until you had a completed AGV, all of you. You had a complex problem situation, you followed this process, and you came back around and created a product that satisfied the customer's need. And you should be very proud of that. That is a great accomplishment that you did this full cycle process and have a working device. So as you go forward in your career, I hope that you'll remember your job as an engineer and the systems. You'll remember the engineering design process. And whether it's a big or whether it's a small design, that you'll remember to follow these steps and let them lead you. That you'll be thinking about these 4 cardinal rules of design as you do that. And that you'll also remember, as you're trying to come up with requirements, you've got some tools that can help you do that. You've got some questions. You've got a process that you can follow to help you. And if you'll do these things, you will find it'll make you a better engineer. It will allow you to take that complex problem situation, to understand that customer, and to turn around and to make them happy. So good luck as you go forward.